Hi, I'm Eric, and this is my submission to MITx's 5th Circuits and Electronics Classmates Contest. For my project, I will go through the design process of a theremin and show you the analysis of key theremin electronic components. First, a bit about myself. I'm a junior in high school, and I'm an active member of the robotics team. I love anything from computers to electronics, which includes programming and circuit design. I thoroughly enjoyed this course, and I look forward to any future courses, especially 6004X in this March. But back to the theremin. Perhaps you don't know what a theremin is. Well, that's okay. Allow me to explain. A theremin is a musical instrument invented by Leon Theremin in 1928. It is a very unique instrument in that your hands never actually touch part of it. You operate it by placing your hands next to two antennas and changing your distance from them. By changing your distance, you change the pitch on the top antenna and the volume of the theremin on the bottom antenna. The sound effects can be very strange and spooky. Now, the antennas do not receive radio signals as you might suspect. Actually, they operate as a capacitor. The antenna itself forms the anode of a capacitor, and your hand forms the cathode, connected to a virtual ground, which is your body. This capacitor is variable, and the distance between your hand and the antenna changes its capacitance. This changing capacitance is what changes the frequency of an oscillator. This oscillator oscillates at radio frequency. Now, your ears cannot hear radio frequency, so a reference oscillator must also operate at a frequency similar to it. In this circuit, the pitch oscillator operates anywhere from 44 kilohertz to 48 kilohertz, and the reference oscillator will oscillate at 48 kilohertz. Now, to make this frequency audible, we have to drop it down to audio frequency. And for our theremin, we're going to operate between 30 hertz and 4,000 hertz, or 4 kilohertz. This is done in a mixer, a process known as heterodyning, which subtracts the frequencies of the two oscillators. But it doesn't just subtract them. It actually makes a new waveform, which is the sum of two sine waves. One is the difference of the two frequencies, and the other one is the sum of the two. So you get a waveform similar to the one I've just drawn. Now, alone this is not audible, and it is audible, but it would be really horrible to listen to. So we need to filter out that high frequency formed by summing the two oscillators together. So this theremin will create a waveform from the mixer that is 4 kilohertz and 92 kilohertz. But once we filter that out through a low-pass filter, only the 4 kilohertz signal will remain. This new waveform, which is a pure sine wave, is then fed into an amplifier. This pure sine wave will be anywhere from 30 hertz to 4 kilohertz, just like we want in the audio frequency range. Now, this amplifier is not constant amplification. It has a variable gain, and this variable gain is controlled by a voltage, and this voltage will eventually come from the volume antenna. And from the amplifier, it goes to a speaker where the music can be heard. Now, the volume antenna operates much the same way. It controls a volume oscillator that also operates at radio frequency. When your hand is very close to the volume antenna, it operates at a very high frequency. As you move further away, the frequency decreases. This waveform is then fed into a bandpass filter. The purpose of this is so that when your hand is very close to the theremin and you have a very high frequency coming from the volume oscillator, the signal is attenuated and it will have a low amplitude. As you move further away into a specific region where the filter has a gain of 1, your signal will have the same amplitude. And then as you move yet further away, as if you were to walk away from the theremin altogether, the frequency would move into a range where the signal would be attenuated and it would have a very low amplitude. This new signal now is fed into an envelope detector, which detects the amplitude of the signal and converts it into a voltage. This voltage is then fed into the variable gain amplifier, and it will control the gain of the pitch the pitch coming from the pitch antenna. Okay, so before we can begin analyzing any one of these components, we need to figure out the capacitance of this and this antenna. Now, to solve for this capacitance, you could use a multimeter that measures capacitance. But I don't happen to have one that can measure in the range of picofarads, and I don't know many people that do. So we have to solve for this capacitance using another method. I do have an oscilloscope and a signal generator, so I concluded that I could hook the capacitor up to the signal generator and measure the impedance across the capacitor. So the circuit looks like this. Vin coming from the signal generator will send a sine wave through a resistor R to the antenna. And this is our output. So the equivalent circuit would be Vin cross resistor R capacitor to V out. Now we can write an equation for this simply using a voltage divider equation, which is V out equals Vin times times C, capacitor C, over R plus C. If we substitute in our impedances, C now becomes 1 over J omega C, which is the complex impedance for a capacitor. So our new equation now is V out equals V in times 1 over J omega C, all divided by R plus 1 over J omega C. Now let's simplify this further. Let's solve for the gain. So we can divide both sides by Vn to give us our gain equals, and let's multiply the numerator and denominator by J omega C to simplify it. So we have 1 over J omega CR plus 1. Now we want to solve for the magnitude of gain. So to do that, we need to move J, our imaginary number J, into the numerator of this equation. And we will do that by multiplying the numerator and the denominator by the complex conjugate, which is negative J omega CR plus 1 and negative J omega CR plus 1. New equation looks as follows: negative J omega CR plus 1 all over omega CR product squared plus 1. Now, if we look at this from the complex coordinate system, the magnitude is this value. And this is the real part of the impedance, and this is the imaginary part. So, using the Pythagorean theorem, we can calculate the gain as in gain squared equals negative j omega CR over omega CR product squared plus 1 squared plus 1 over omega CR squared plus 1 squared. So get rid of this exponent. And we can now solve for our gain as, no, this j isn't supposed to be there. We know the gain from this circuit, V out divided by V in, is going to be equal to this expression in terms of omega being the frequency times 2 pi, and C equaling the capacitance of our antenna, and R equaling the resistance of this resistor. So let's go see what this looks like on the oscilloscope. This is my setup. I have a signal generator here generating a sine wave at 20 kilohertz. I have that signal hooked up to a resistor here, which then goes to this aluminum sheet. And this aluminum sheet will form my capacitor slash antenna that we're trying to measure the impedance of. So if we look at the oscilloscope, we can see that channel A is hooked up to the input, which is at exactly 20.00 kilohertz. Let's measure the voltage there. So, and the voltage is 6.4.5, it's about 6.5 volts. Now, let me measure the voltage at the capacitor, across the capacitor, or the antenna for that matter. And, 1 second. And as you can see, when my hand is far away from the antenna, we are getting 1.42 volts. If I were to move my hand closer to the antenna, as if I was about to touch it, we get 1.11 volts. Okay, so now we have the values from the setup. We know the equation, as we just solved for. We know omega is derived from 20 kilohertz times 2 pi. Our resistance was 4.88 mega ohms, and these are our V outs and V ins. And remember, the 1.42 volts was when our hand was a meter away, and the 1.11 volt was when our hand was a centimeter away. So to evaluate this expression for C would require a lot of grubby math, but I just did it on my graphing calculator and just solved for the x-intercept, and I got a capacitance of 7.27 picofarads when my hand was a meter away, and 9.4 picofarads when my hand was 1 centimeter away. Now, to model this situation, it's not so simple as saying our hand, as illustrated, and the capacitor, and the plate. We can't just say this distance must be inversely related to the capacitance, as the capacitance equation shows. C equals epsilon, the coefficient of epsilon, the dielectric coefficient, times the area of the plate divided by the distance. Well, it would appear that capacitance is equal to some constant k divided by distance, which could easily be calculated from this expression. So let's evaluate that. What is k for this expression? We get 7.27 picofarads times 1 meter. And for this situation, our k is equal to 7.27 times 10 to the negative 12th. But if we evaluate k for this situation when we were a centimeter away, let's do that. 9.4 picofarads times 1 centimeter. It is k equals 9.4 times 10 to the negative 14th. So this does not accurately model the situation. A better model will be the capacitance at the antenna, which is what we read here and here, is equal to this constant k divided by our distance plus a capacitance being read from the world. So I'm going to call this the world around it, the table, the lighting fixture, any object that's forming a capacitance near the antenna. So let's just call this world. So now we should be able to solve for k and the capacitance of the world using these two data points. So using a system of equations, it evaluates that the capacitance of the world, C world, is equal to, calc intersect. Yes, so C world is equal to 7.25 picofarads, which is very close to when our hand was very far away from it. And the K, which is our coefficient for the capacitance, is equal to 7.249 times 10 to the negative, oh, wait, never mind. That is the wrong value. Is equal to 2.141 times 10 to the negative 14th. Now we'll use these values when we're trying to linearize the output sound, which is very important for a theremin, because as you can see, the capacitance is not directly related to the distance, so that's not linear. Then we'll find that the frequency of our oscillator is not directly related to the capacitance, so that is also not linear. And then we'll find that the octave we're in when we're trying to create a certain sound is not directly related to the frequency. It's actually logarithmic. So all of these different values are making this very unlinear situation. So we need to optimize our values so it looks like it's the most linear. We'll never get it perfectly linear, but we want to make it so the further as our hand moves in, the change in pitch, or the change in tone, the output by the theremin is very linear. Okay, let's look at the oscillator circuit now. Now all three oscillators are going to look similar to this. They're going to have a relaxation oscillator hooked up to a low-pass filter, and this will generate a pure sine wave. Now this capacitor here is what we'll be controlling, whether it's either the antenna for the pitch or volume oscillators, or for the pitch reference oscillator, it'll just be a tuning capacitor, a trimming capacitor, I mean. There are a lot of ways to generate a sine wave controlled by a capacitance, and this is probably a very inefficient way to use a relaxation oscillator, but I chose to use a relaxation oscillator just because 6002X students should already be familiar with it. Other ways would include a Weinbridge oscillator would produce a sine wave, or a Colpitts oscillator. Those would be common oscillators used in a theremin. But nevertheless, let's just work through this. Let's try to find the frequency equation in terms of capacitance and the resistance. resistance R1. For starters, R2, these are both R2 values. They're set equal to each other. And let's begin. So let's assume that this V out pin, let's just call this node V out, starts at ground. Let's call this V minus starts at ground and V plus starts at ground. But there, of course, will be random noise in working at all these pins. And let's assume that at one point in time, the positive pin, the V positive pin, becomes slightly more charged than the V negative pin. If this were to happen, and this were an ideal op amp, this would cause the output to shoot up in voltage. And this will amplify the output voltage because of positive feedback, and instantly the V out will shoot all the way up to Vs. So it'll go from 0 to Vs almost instantly. Once that happens, and this is in terms of time, the V plus pin will shoot to Vs plus divided by 2. Now this happens because there is a voltage divider circuit with the two resistances, and since both resistors are set equal to each other, the voltage across the last resistor is Vs divided by 2. Now let's look at the above part of the circuit, and that should look very familiar right now. It is Vs into a resistor and across a capacitor into ground. And this pin right here, the V negative pin, is equal to the capacitance and the voltage across the capacitor. So this is V negative. Now we should be able to model the voltage of the V minus pin as a function of time by V minus of t is equal to Vs times 1 minus e raised to negative t divided by the time constant tau, or Rc. If we start to graph that, it will look something like this. Like familiar Thevenin equivalent function of time versus time with a capacitor there. But it does not keep going to Vs plus like you'd expect. Actually, as soon as it gets to Vs divided by 2 right here, it stops rising, and this is what it would like to do but does not, because as soon as it gets slightly above that voltage, it now becomes greater than the V positive pin. So it has a greater voltage than that. When that happens, that inverts the output, and this output drops to negative Vs almost instantly because of positive feedback. So then if we look at the V positive pin, that drops to Vs negative divided by 2 as well. And let's now look back at the V negative pin. So now this is Vs negative, so V of t will equal this new function, V minus in terms of t will equal, since it starts off at Vs divided by 2 plus Vs over 2 plus minus the new voltage, which is Vs minus Vs positive over 2. This times 1 minus e raised to negative t over Rc. So again, we can graph this, and it should look familiar. And it will want to look like this over the long run, but it does not, because once it gets to once it equals the V positive pin again, the whole op-amp output inverts once more, and the capacitor stops charging again. And this cycle repeats indefinitely, as we should all be familiar with. So now we just need to derive the time period it takes for the capacitor to charge up, to discharge, charge up, to discharge, so we can calculate the frequency. To calculate this value, we just need to evaluate this expression for t when V minus equals the Vs over 2. Once it equals the positive pin of the V positive of the op amp. And then that expression for t is equal to 1/2 of the total period of oscillation period. So 2 times that t is equal to the period, and frequency is the inverse of the period, so 1 over 2t equals our frequency. Now this t evaluates for ln of 3. I'm not going to do the math. It's just a lot of grubby math, so I'll just tell you the answer. T equals ln of 3 times RC. So the frequency of this oscillator is equal to 1 over 2 ln of 3 RC. And to prove that this does work, here's a relaxation oscillator I built, and it has a 4.88 mega ohm resistor and a 100 nanofarad capacitor. So that should have an oscillation of 0.93 hertz, but it in fact has a 0.87 hertz. But I'd say that's pretty close. So with that, we can move on to the low pass filter. So we'll be sending a square wave with the frequency 1 over 2 ln of 3 times RC. And we want to turn the square wave into a sine wave. So this is the gain equation that we calculated earlier. And this equation is specific to this circuit where the low pass filter, which is a resistor hooked up to a capacitor. And we're measuring the voltage across the capacitor divided by the input voltage. This equation is in terms of omega. So we are trying to filter out the higher values of omega, which will be the higher harmonics of the square wave, and we're trying to attenuate those, or we're trying to retain the fundamental frequency of the square wave, and that is the output frequency we would like. So our input frequency, our input waveform is going to look like this. We want our output to be the same frequency and the same amplitude, or a similar amplitude of the sine wave type. We know, because of the Fourier series, that this square wave is actually a sum of multiple sine waves. So you have the fundamental frequency, which is this sine wave, but it's also the sum of a frequency 3 times that of the fundamental frequency and a third of the amplitude. And we also know it's in addition to that, there's a frequency 5 times the fundamental frequency and also a fifth of the amplitude. So we want to solve for our resistances and capacitances of the circuit so that we maintain this signal and attenuate these signals. So the cutoff frequency for an RC filter, mega cutoff, is equal to 1 over RC. We want our cutoff frequency to be, let's say, 60 kilohertz, because our square wave will be anywhere from 44 to 48 kilohertz. 48 kilohertz. And our second, so this sine wave will be, we want it to be 44 to 48 kilohertz. And the next frequency down will be 3 times that, so it'll be 132 kilohertz to 48 times 30, 144 kilohertz. So let's choose a cutoff frequency of 60 kilohertz and see what that does for us. So if we say 60k times 2 pi for our angular frequency and set that equal to 1 over RC, and let's just arbitrarily choose an R value. I'll choose let's say 1k. So with R equal to 1k, our C value, so 1k equals R, C equals 116.7 nanofarads. So with those values, we can then graph the gain versus the frequency of going into the filter, as I have done, and you get a function that looks like this. So if we trace this function, let's just second calc at 48 kilohertz, we have a gain of 0.78. So 78% of the original amplitude will be passed through at 48 kilohertz. At the third, 3 times the fundamental frequency, it shall be like 132 kilohertz. So let's second calc 132. Okay. The gain will be 41%. So it'll attenuate the 60% of the signal. Now, this will give somewhat of a sinusoidal function, but I prefer to filter this 3 more times, as we do in the generator, and that'll give us a much more sinusoidal waveform. So let's put in 1K for all of these resistors, and this is 16 nanofarads for all of these. But by the time the waveform, the sine wave, gets to the mixer, it's been attenuated considerably, because the gain, even at 48 kilohertz, is still what was it, like 80% gain? I mean 0.8. Second calc value 48. Yeah, it's 78%. 0.78 is our gain. So we have to then amplify that signal, and here is just a inverting amplifier circuit. So which should equal the gain of this circuit is equal to, this is R1 and this is R2, I believe negative R2 over R1 times the negative R2 over R1. So whatever signal we lose by the time we get there, we want to amplify that. And rather than using 2 resistors, it would make more sense to just use a potentiometer right there. So I believe it would look like, so we have a potentiometer that will be adjusting this inverting amplifier. So now we have a relaxation oscillator creating a square wave which then gets fed through this low-pass filter, and the fundamental frequency of this square wave is then passed on to this amplifier for it to be sent to the mixing stage, the heterodyne process. So here's the relaxation oscillator with two low-pass filters hooked up to it now, and the output is being fed into the oscilloscope. One major difference, however, is the relaxation oscillator's frequency has changed. I changed out the capacitor for the aluminum foil plate, which will be the antenna, and I believe I changed out the resistor to 100K. It might not be 100K, it might be 4.88 mega ohms. But as you can see, when my hand is very close to the, far away from the oscillator, it's at 198 hertz. But when I move my hand very close to it, I can get up to almost 600 hertz. So up until this point, I've been referencing the 44 kilohertz frequency from the pitch oscillator. And I haven't really explained why 44 kilohertz. Well, this graph should. This, on my y-axis, will be the pitch of the theremin creates in terms of measured in octaves. And on this axis is the distance my hand is from the antenna. So up here is the equation that models this, and within these brackets is the frequency. So I'm taking the common log divided by the log of 2 because it's actually a log base 2. I just can't do that in on the Mac grapher. But that's because octave is logarithmic function of frequency. From there, I subtract the frequency of the pitch oscillator, this oscillator, in this expression, from the reference frequency, this expression. This should look familiar, 2L and a 3 times this expression right here, and that A is resistance, so that's the frequency. And then within that is the expression for the capacitance, either the capacitance of the reference oscillator or the capacitance of the antenna itself. And if you look at the schematic for the each oscillator, it's not the antenna does not operate by itself. There's a capacitor in parallel with the antenna to ground, and that would be this C value right here and here. So from this expression, I define that capacitor in parallel, and I define it right here as 20 picofarads. So that's going to be in parallel with the antenna. Now these values, 5.051 times 10 to the negative 14th, that is the K value I defined yesterday. That K value is different than the one I defined in this video, and that is probably the result of changing humidity, temperature, and other various factors. And this 25 times 10 to the negative 12th is 25 picofarads, which I calculated for the capacitance of the world, which is very different than the one we calculated today. So from that, I define this C value, and then I define the resistors R and R1, R of the pitch oscillator and R of the reference oscillator. And when you evaluate all of this, you get a frequency that ranges from 44 kilohertz to 48 kilohertz. So it's very specific. And this is the linear part of the graph that we're concerned with. So from when I'm 4 decimeters away from the antenna, I'll be at 5 octaves, and when I am almost a centimeter away from the antenna, I'll be at 12 octaves. And that gives a good range of motion. So this is the equivalent of 30 hertz to 4,000 hertz. Well, having gone through the oscillators, the next step in the progression would be to the mixer. But to be honest, I do not have the transformer necessary to build that circuit. It's in the mail, but it has not come yet. So rather than waste your time, I'll move past that and then come back if I have time later. After that will be a low-pass filter, and we've already gone through calculating that. So let's skip past that and move down to the volume oscillator. No, we've already gone volume oscillator, but the volume part of the circuit. So let's move on to the bandpass filter. Alright, so now looking at the volume part of the circuit, we have our volume antenna controlling this volume oscillator. Now, just arbitrarily, let's say the volume oscillator operates from 200 kilohertz to 220 kilohertz. And let's say that the distance we want to put our hand from the antenna gives a frequency of 208 kilohertz. And that distance you want to be the loudest. If you move further away, it'll become quieter. If you move closer, it'll become quieter. So we're going to run this frequency through this band pass filter. And we want at 208 kilohertz to have a gain of 1 and pass it through. And anything further away from that, we want the amplitude to slowly decrease. So let's take apart this circuit and let's redraw it with the impedance values. So we know the resistor is just R1. Capacitor is 1 over J omega C. And then this will be our output. We have capacitor 1 over J omega C 2 and R2 there going to ground. So our equation will look something like this. V out equals over V in equals 1 over J omega C squared, C2 times R1, R2, not times R2, I mean plus R2. Over, no, did I say plus? I mean in parallel with R2. Over R1 plus 1 over J omega C1 plus that expression. 1 over J omega C squared, C2 in parallel with R2. So let's expand this out, and that is 1 over J omega C2 times R2 over 1 over J omega C2 plus R2 over R1 plus 1 over J omega C1 plus 1 over J omega C2 times R2 over 1 over J omega C2 plus R2. So there you have it, and that is the gain of this bandpass filter. I'm sure there is a much easier way to get that value, but that is the only way I could solve it. And this is the equation plotted versus frequency, and the gain is on the y-axis. The RC values are completely arbitrary. Well, I'm going to have to stop there. This is all the time I have. It's a school night tonight, and I need to be getting to bed. So I guess this concludes my submission to CECC5. I hope you enjoyed my video, and I'm really disappointed I didn't get to cover more and go more in depth. And I'm also sorry that it took so long to cover so little. I do intend on building this Theremin once the parts arrive. The USPS is still shipping them, and I was hoping to have the Theremin built for this video, but that cannot happen. I'll post a link of the completed Theremin video in the comments or video description when it does get done, but this is all I have for the competition. I hope you enjoyed the video, and again, I apologize I did not get to cover the entire Theremin. Bye.